We're going to finish notes for chapter 3.2, mean value theorem and Rolle's theorem. So let me read through Rolle's theorem. Now, Rolle's theorem is basically just a subset of mean value theorem. If you know mean value theorem, then you know Rolle's theorem. Rolle's theorem is just a very specific instance of mean value theorem. So if a function is continuous, okay, no breaks in the graph, differentiable on the open interval, so the conditions are exactly the same as mean value theorem. But now there's an additional condition, and that is where the endpoints have to be equal. So the endpoints have the same y value. Okay, then there must be at least one point in the function where the slope of the tangent line is 0. So in other words, if the endpoints have the same y values, then we can guarantee a relative maximum or a relative minimum somewhere between the endpoints. Okay, so again, Rolle's theorem is just a very specific instance of the mean value theorem. So if we think about mean value theorem, what we say is that if we have a smooth curve, continuous, differentiable, whatever the slope is between the endpoints, then there must be, with mean value theorem, we say that there must be at least another point on the graph where the slope is exactly the same as the endpoints. Now, if we have the additional condition for Rolle's theorem where the endpoints the y values of the endpoints have the same are the same, then the average slope between those two endpoints will always produce 0, right? If the y values are the same, then change in y over change in x will always be 0. So if we get an average slope of 0, then we can guarantee that somewhere between the graph there must be another average slope of 0, or another a point that is tangent to the curve where the slope is 0. Okay, so many times we're looking for max and mins of a graph, so that's why there's a specific case to look for that with Rolle's theorem. Okay, but essentially, this is the same thing as mean value theorem. It's just that we're now looking for where the slope is 0 on the graph. Okay, but to guarantee that, we need the endpoints to also have the same y values so that the average slope will produce 0. Okay, so the steps we go through our continuity checks, no breaks between graphs, differentiability, smooth curve between endpoints, and again the way we tell that is we find the derivative, look to see is there any part of the denominator that will cause the derivative to be undefined, or with absolute value functions. That's also another potential instance where differentiability could fail. Again, polynomial functions are continuous and differentiable everywhere. Don't need to think twice about that. We can just state that. Okay. The next step we test endpoints. Does our y values at endpoints and the y values, are they the same? If they're the same, then we can guarantee that the slope will be 0 somewhere between. If not, then Rolle's theorem fails. However, mean value theorem could still apply, but if we're just talking about Rolle's theorem, the endpoints have to agree in order for us to guarantee that slope of 0. Okay. If yes, then we set our derivative equal to our average slope. In this case, our average slope will always be 0 if the endpoints agree, and then we solve for x. Okay. Example 2, determine if Rolle's theorem can be applied to our function on the closed interval from 1 to 2. If so, find the value of c such that f prime of c is equal to 0. We have a polynomial function, so we know the function is continuous and differentiable on the closed interval. So next step we do is we take the endpoints, plug them into the original function, and see if we get the same y value, because we want to see if Rolle's theorem is going to pass. So f of 1 gives us 0. Okay, f of 2 gives us 0 as well. Now we're not always looking for zeros. We're just making sure that these have the same y values. So it just so happens that these are equal to 0, but it could be 5 and 5, it could be 8 and 8. But as long as these have the same y values, then we can guarantee that Rolle's theorem will pass. So, and then to show that this is essentially mean value theorem, we just do change in y over change in x, we get 0. So now we can guarantee that the slope will be, that there's going to be a point on the curve where the slope is going to be 0. So we set our derivative equal to our average slope, just like mean value theorem. It's just that now our average slope is always 0. Our derivative is simply 2x minus 3. We go through power rule, set our derivative equal to the average slope. In this case, it's always 0. So x equals 2x equals 3, x equals 3 halves. So we have c value of 3 halves. Make sure it does lie between our endpoints of 1 and 2, so our C value is guaranteed. Okay, example 3, determine if Rolle's theorem can be applied to the function 3 minus absolute value of x minus 3. Now let's graph this function. Absolute value of x minus 3 is simply going to be a absolute value function where the vertex is at 3, 0. In this case, it'll be at 3, 3. Okay. The graph is going to open downward because of the negative. So we can also think of it this way. If I write it as y is equal to negative absolute value of x minus 3 plus 3, maybe that's in the form that's a little bit easier to recognize. So vertex is at 3, 3, opens down, and a slope of 1 because we don't see a number, slope of negative 1 rather. So from 3, 3, we graph down 1 over 1, down 1 over 1. We have our absolute value function. Is the function differentiable at x equals 3? We see the function is not differentiable at x equals 3, and that is going to impact our endpoints. So we know that even though the function is continuous, the function is not differentiable between the endpoints. So therefore, we have to say that Rolle's theorem is going to fail because it does not pass the differentiability condition. So Rolle's theorem does not apply.